part 2 of section 3.1, characteristics of polynomial functions. I hope you remember from last day that I really wanted you to pay some careful attention to that little chart that we created. So let me just go back there really quickly. Yes, that's this one here. Remember how I asked you how are the degree of the function, the sign leading coefficient, related to the general shape of the graph? Well, just as a quick review, remember odd degree polynomials. If the leading coefficient is positive, the graph begins in quadrant 3 and then it ends in quadrant 1. Okay, so you gotta know that. And if it's negative, the graph begins in quadrant 2 and ends in quadrant 4. Now, if you can't memorize it, the good way of understanding odd degree polynomials is use this idea of x to the power of 1. I hope we all know what that looks like. If y equals to x, that would be an odd degree polynomial that has a leading coefficient that's positive. Well, the graph of that is very simply just a straight line going upwards. And notice it starts in quadrant 3 and ends in quadrant 1. So, if it works for x to the power of 1, it's the same for x to the power of 3, it's the same for x to the power of 5. Okay? Whereas, if the leading coefficient is negative, I look at y equals to negative x. And I know for this graph, of course, the graph goes downwards. So it always starts in quadrant 2, then ends in quadrant 4. Okay? Once again, odd degrees start and end in different locations. If it starts low, it ends high. If it starts high, then it ends low. So for even degree polynomials, if the leading coefficient is positive, and the sample I always think about is y equals x squared, well, that's that parabola we learned in grade 11. And so, well, what do we know about the parabola? Yeah, it always begins, if you're going from left to right, in quadrant 2, and then ends in quadrant 1. Okay, and then I think about the negative x squared graph when I talk about an even degree polynomial where the leading coefficient is negative. And this once again illustrates that going from left to right, it begins in quadrant 3 and ends in quadrant 4. So keep those in mind now as we try example number 3. So in number 3, I'm going to ask you to now sketch the polynomial function with a given characteristic. So given piece of information, can you make a quick sketch of what the graph actually looks like? Okay, so we're kind of going backwards from example number 2. Alright, so let's take a look at example number 3a. You've got a polynomial function with degree 4, a negative leading coefficient with 4 x-intercepts. So let's take a look at what data we have here and see if we can come up with a sample sketch. I'll draw the axes for all of them first. And remember, these are sketches, so they don't have to be exactly accurate, and there may be more than one answer. Okay? Okay. So, what do we know about A? Degree 4. So, even or odd, you should ask yourself. Right, even. So, knowing that it's even and it's a negative coefficient, how does the graph start and end? Well, which quadrant does it start? Which quadrant does it end? Even and negative coefficient. Think about the negative x squared graph. And if you said it starts in quadrant 3 and ends in quadrant 4, you are correct. So you know it must start here in quadrant 3 and it must end here in quadrant 4. Okay. Now the next part says there are 4 x-intercepts. That means it crosses the x-axis 4 times. So if I were to extend this graph, I guess it must cross once. If I extend this, it must cross twice. Well, there should be how many? Yeah, there's 4, so maybe I'll put one here and one here, and what should you notice? Well, I guess it comes back to intersect. This one can come back down to intersect, and then this must join like that. I think this is a perfect example of a polynomial function with degree 4 and a negative leading coefficient. Okay, I'm going to try part B with you as well, and then I want you to try C and D on your own, okay? You can come back and check your answer. Polynomial function with degree 3 and a negative leading coefficient with 2 x-intercepts. Alright, so once again, let's analyze this. Degree 3, negative leading coefficient. Where do we start? Where do we end? How about quadrant? Yes, 2, ending in quadrant 4. Okay. Up here, then down there. Alright. This one says there are 2 x-intercepts. So, knowing that there are 2 x-intercepts, I guess here's one. I'm going to connect like this. Here's another one. I'm going to connect like this. Now what? I gotta connect them together somehow. These two dots. What can I do? Well, here's one answer. Okay. If you didn't like that, you could have also had this answer. Let me erase this. Could have also done this. Okay. Either or works. Now notice this graph has a place where the graph comes up and just touches the x-axis and then goes back down. Okay, doesn't actually cross. And in this case, and I'm going to give you a little hint as to what's to come, we call this a double root. Okay, just imagine if I had 2 roots. Don't write this down, just watch. 2 roots, and this one got closer and closer to the one on the right. So the 2 roots actually lie on top of each other, and therefore that's why the graph doesn't cross the x-axis. It just touches and comes back down. Double root. Okay? Stay tuned for more of that later on. Alright, as promised, you try C and D. Okay, so these are just 2 examples of what you could get. If you're not too sure if yours is actually right, bring it back to class and I'll take a look at it with you. Okay, but these are just some samples. Alright, let's turn the page. Last example for this section. It's a pretty long section, I know. Yes, lots of interesting material. Okay. By the way, for those of you who are taking calculus, this is a question that you should know and you will see again. So please pay careful attention, okay? Even though you're not taking calculus right now, if you're planning on doing any college or university level of math, you will see this again, okay? So let's do this one. I'm going to ask you to read this on your own and then see if you can answer these questions. The interesting stuff comes in parts E, F, and G. In the meantime, A, B, C, D, E, I think are straightforward. Okay. So I've got a puppy. He moves forward and backwards along a straight path. So imagine him on the sidewalk. Okay. Here's my sidewalk. Here's my puppy. Woof woof. Okay, doesn't look like much of a dog, but whatever. Okay. I don't know what that looks like now. Here, dog. Somebody help me if you know how to draw. Anyways. So the puppy's distance in d meters from a tree is modeled by this polynomial function d of t. So the distance is affected by its time. and it's given by this equation, t cubed minus 6t squared plus 9t, where t represents time. Okay, so what is the degree, leading coefficient, and constant of this function? Well, the degree would be, looking at this function here, yes, 3. The leading coefficient would be, yes, 1. And the constant of this function, that means the one without the t's, well, it's actually not here, right? This doesn't exist, so you can either say the constant is 0, because it doesn't exist, or just say no constant. Both will be okay. Well, here's the next question. What does the constant actually represent? So what does this 0 actually represent in this situation? Well, remember the constant is when, I guess, t equals to 0. So when t equals to 0, this distance away from the tree is also 0. So think about it. I guess this dog is starting at a point where he is right next to the tree. Okay? So this is his starting point. Okay? Now, when I talk about end behavior of the graph of this function, I'm saying what happens when t gets really big, okay? T becomes very large. Well, I guess you'll say as t becomes very large, what happens to d? The distance d becomes, well, let's think about this. Let's plug in a big number like 1,000. 1,000 cubed, that's a lot. Minus 6 times t squared, that's a lot, but not as much as the cubed plus 9t. Well, it looks like it's getting big too, so the distance d also becomes very large. Okay, and if you like the calculus term, we'll say it approaches infinity. Okay. Now, if you're curious about restrictions on the domain of this function, what do you think the restrictions are on the values of t? Yeah, if you said that the restrictions on the domain of this function is that t has to be bigger or equal to 0, you're correct. We're talking about t, which is time. I wish I can go back in time. I wish I could be a high school student like you guys now, with no carefree worries in the world. Okay, I'm joking about that, I know, but you know what? Much easier than being an adult. Okay, so the time has to be bigger or equal to 0, right? Because you can't go back in time. Okay. Well, how far is Mr. Lee's puppy from the tree after 1 second, 2 seconds, 3 seconds, and 4 seconds? So, can you tell me what my puppy is actually doing as time passes by? Well, you're going to have to use that equation here, d of t. After 1 second, that just means I want to find d of 1, and we're just going to plug it in. So that's 1 cubed minus 6 times 1 squared plus 9 times 1. And that would be equal to, let's see, 1 take away 6 plus 9. How about 4? Okay, going to do the same thing with 2. Okay, and you can use your calculator for this. I think it's 2, and then d of 3. 3 cubed minus 6 times 3 squared plus 9 times 3. 20, 27, 27, 54. I think this one is 0. And at d sub 4, or after 4 seconds, 4 cubed minus 6 times 4 squared plus 9 times 4. I believe that equals to 4. Okay, double check my work, but I believe those are the numbers. Okay. So after 1 second, he is 4 from the tree. So I guess he's traveling like this. This is 0, so 1, 2, 3, 4. So whee, after 1 second, t equals to 1. Doggy is at 4. And then what happens? 2 seconds, he's back at 2. So guess what? Stopped, he must have forgot something. Or he looked back and was so sad that he was away from the tree. So he started going backwards. Okay. Maybe he really wanted to go back to the tree because after 3 seconds, he's now 0 away from the tree. So yes, looking at my diagram here, Dougie's now back at the tree. T equals to 3 seconds. And then what happens after that? I guess D sub 4. Oh yeah, he's like, okay, I'm safe now. Forget this tree. This tree is boring. Let me move away from the tree. And at 4 seconds, it's here. And remember how I said earlier what happens when the end behavior of this graph is taken into place? Yes, as when t goes to infinity, then the distance d becomes very large. So I guess what that means is that this graph just goes on and on and on and on forever and ever. He just runs further and further away from the tree until he's never ever going to come back. Okay? So that's what this equation describes in terms of my puppy's movement along a straight line. Oh, sketch the situation using your info in part E. See picture above. Okay. Alright. Then I said graph the function using technology, and I'm going to ask you how to compare this graph to this sketch. So let me just bring up my graphing calculator now. Okay. We're going to graph out this equation, which is, let's see, I think it was t. Well, we can't use t, so we just use x. So x cubed minus 6 x squared plus 9x. And let's graph this out. I'll try to change my zoom. Let's go zoom standard. Okay. There you go. Now, which part of the graph am I really concerned with? I'm not concerned with the stuff where t is less than 0. So ultimately, I don't care about this stuff that's to the left of the y-axis, because our restriction in this question is that I can't go back in time. So you think about the graph that we have from the graphing calculator. Yes, there's this part down here, but all I'm really concerned about is this part. Okay. Now, how does this part compare with the picture from above? So in this graph, I guess this is 0, and this is again at 0. And if I were to be curious about what this part here is, let me just go find the maximum. At 1 second, it's 4, right? 1, 4. Really, this is not t, but it's actually, sorry, x. It's actually t, and this is d. So you think about this, what we've here done is we've looked at graphing out two variables and comparing d with t. The graph from above is really the exact same thing. It's just it's sideways, right? Distance is now horizontal. Time is the stuff that's going upwards. So I hope you can see that it's the same. It's just done sideways. Okay, we're done. Thanks for listening.